Hi, my name's Seth Thomas, and I'm joined today by Abhi Pachala, Carolina Carlton, Huda Shakur, and Matthew Crane. And we are Team 9, just outside Philly, Inc. And we are the Chemi 470 group that designed the paraxylene production plant for Knitline Chemicals. Knitline Chemicals came to us and asked us to explore a process using a new zeolite catalyst that they found in order to increase the production of paraxylene using toluene. With a flow rate of toluene of 96,500 pounds per hour, we are able to produce 104 million pounds of product per year as our plant capacity. Our main product is paraxylene, or p-xylene for short, with a 99.9% weight mass purity. The second product, benzene, has a 99.9% purity as well. Our plant location is in Houston, Texas, as Knitline Chemicals already had an existing plant with a lot of existing infrastructure for us to utilize. The only thing that we needed to do is develop the site for the actual p-xylene plant itself. Our R&D location is located here in State College, where we did a lot of the process design work. The plant life has some important dates to note. The construction will begin in 2020 and last until 2023, with startup occurring in 2023 as well. The total plant life will be 15 years and will end in 2038. Our process design had to meet a few specification goals in order to be considered successful. For example, p-xylene product purity needed to be 99.9%, benzene product purity the same, and toluene product purity must be 99.5% if we were to sell toluene. Our after-tax rate of return would have to be 15% to be considered a successful plant, while our toluene recovery after the reactor would have to be 85% through the separations. And finally, our benzene, toluene, and paraxylene loss needed to be less than 3% to be considered successful in the eyes of Knitline Chemicals. Our presentation will focus on three main points. The first is our process design and our equipment design, where we talk about how we went through the process flow and how we designed our equipment to meet the specifications needed. The second is an economic evaluation with a sensitivity analysis to determine the feasibility economically of our product and our plant in total. And finally, we'll make some recommendations and some future work recommendations in order to produce the p-xylene that we need with a feasible outcome.
The process operates in two main phases, synthesis and purification. For our first phase of synthesis, we covered just our reactor, and within our reactor is our main phase, toluene disproportionation, followed by two side reactions, toluene hydrodealkylation and xylene disproportionation. And then moving on to our second phase, we then have our purification, which covers a VLE separator, 3 distillation columns, and a Parex. As you can see, this is our BFD, which we'll expand in just a few seconds. We have our toluene feedstock combined with our hydrogen feedstock to go into the reactor. From there, we have our products, which will then go into the VLE separator. With the VLE separator, we hope to separate our light gases from the rest of the feed so that we can have better distillation products from our distillation columns. And so as you can see, for our first distillation column, we have benzene leaving the top of the column as a distillate, and it's also equipped as a partial condenser, so we can then vent the light gases out from the top as well. So just in case if we have any residual hydrogen or methane, it can leave our process. That's followed into our toluene distillation column, where we are able to remove 99.9% of our toluene, and then our TMB column, which removes all TMB. And that allows us to have an enriched feed into our Parex, where we can then have our purified product. So the reactor utilizes zeolite, a new catalyst to convert toluene to mixed xylene isomers with the high selectivity to p-xylene. And so what we saw with traditional catalysts is that there's a selectivity of 24% to p-xylene, while our reactor is actually capable of achieving 34%. And so that is why we decided to use zeolite as a new catalyst. Our reactor contains 13,000 pounds of catalyst and has a length of 14 feet and a diameter of 5 feet. And as you can see, we have our hydrogen feed combining with our toluene feed in order to reduce coking within the reactor. And then we have our products, which are the mixed xylenes, benzene, TMB, which comes from a side reaction, toluene, hydrogen, and methane, which also comes from a side reaction. Distillation separates the benzene, toluene, and TMB from mixed xylene isomers. So first, what I covered before was that the benzene column is equipped with a partial condenser, which removes any residual hydrogen and methane from the process stream. And then followed by that is the toluene column and then the TMB column. All three columns are under 200 feet, and they also have a diameter of roughly about 10. The P-xylene is then separated from the O and M xylene isomers using the Parex adsorption unit. The conditions were set by Nitline Chemical for 320 Fahrenheit and 95 psia. That was in order for the column to work correctly and for it to achieve the correct separation.
The job plant meets most of the specifications that are demanded by Nitline Chemicals. So the product purities for P-xylene, benzene, and toluene are met. The toluene recovery specification is not met because there's no toluene recycle in the process. The benzene toluene paraxylene loss is also not met because there's no recycle of toluene. And the after-tax rate of return is also not met because we are in a deficit. So the plant uses three types of control schemes to maintain proper process operation. So there's the temperature control, the level control, and the pressure control. The temperature control is used to maintain the temperature of the process stream exiting the heat exchanger, and it basically varies the flow rate of the utility. The level control maintains the liquid level in the tank. If the liquid level is too high, then the rest of the plant downstream of it will be backlogged. The pressure control maintains the pressure in the column because if the pressure is too high, that could cause explosions within the column. In addition to meeting the product purity specs, the plant also meets the safety specifications required by Nitline Chemicals. The first one is the benzene safety specification, where the storage tank for benzene is kept far away from a natural river source, which prevents contamination. The second specification is the hydrogen and methane gas purge. It's kept away from an open flame or anything explosive to prevent explosions. The third one is the TMB flare. And basically, the TMB flare converts TMB into CO2 and hydrogen into water vapor. And the ppm of CO2 leaving the flare is kept under 40 ppm. The OBL site, there's an OBL site that is used to store raw materials and products 1 mile from the plant. On the left-hand side of the screen, you can see our steam generation OBL site. We use high-pressure steam, medium-pressure steam, low-pressure steam, and low-pressure steam to supply utilities to our plant. And on the right-hand side is the dimensions of our OBL toluene tank, which has a volume of 334,000 feet cubed, and the storage time is 7 days.
After we analyzed the design of our plant, we looked at the economic viability of building this plant and whether it would turn a profit. So our plant capital is estimated at $165 million, and that includes our IBL and OBL costs. Currently at market price, we can sell our P-xylene and benzene products for a total of 84.6 cents per pound, and we are also making a net gain of 8.62 cents per pound by selling our steam that we make as well as our TMB as fuel. In our pie chart, you can see the cash costs of operating the plant, and this consists of our raw materials, our utilities, our fixed costs, and the SG&A. So the raw materials takes up the vast majority of our cash costs, and this leads to a total cash cost of $2.48 per pound of product. So we're spending $2.48 to make 1 pound of our product. We also took a closer look at our IBL capital costs, and we found that the Parex unit takes up a vast majority of this cost as well at $56 million of our $92 million estimation. So this is the most expensive piece of equipment that we will have to install. In order to be profitable, we need to take a closer look at our raw material costs. So we found that 85.2% of our cost is our toluene feed. So this comes out to about $2 of toluene per pound of product that we make. And since we're selling our product at 84.6 cents per pound, this is not viable. So in order to decrease the amount of toluene that we use per pound, we need to make a higher conversion of our product and make more P-xylene. Finally, we looked at the cash flow, and we found it to become increasingly negative for each year of operation. Our net present value over 12 years was negative $146 million, which is a very large amount. We want to be making money and not losing money. We didn't have an interest rate of return, so we did not meet our 15% ATROR as specified by Nitline Chemicals. And in order to meet 15%, we would have to be selling our product at $6.30, which is much higher than market value today.
Since the plant cash flow is negative, sensitivity studies has been conducted in order to determine the correct economic condition. The first one is by varying the price of natural gas. Price of utility cost is calculated based on the price of natural gas. As we can see from the graph, as we increase the price of natural gas, the cash flow will decrease. So it can be concluded that this option is not feasible, as there is a possibility that the price of natural gas might be increased in the future. The second one is by varying the fixed cost, which is the operating cost. From the graph, the less we pay the operator, the more money we make. However, this option is not recommended, as the operator might go to the other company who pay higher salary per hour. The third option is by varying the price of raw material, which is toluene. From the graph, if we increase the price of toluene, the cash flow will decrease. Again, this option is not feasible, as the price of toluene might be increased in the future. The fourth one is by delaying the start-up year. Delaying the start-up year until 2027 will increase the cash flow. However, after 2027, the cash flow will decrease. So it can be concluded that this option is not feasible. All these four studies have been conducted at current product price, which is around 84 cents per pound. In order to make this plant profitable, the product price needs to be increased. PDRI is a tool to measure project scope of completeness. A total of 3 PDRI analyses has been conducted throughout the lifetime of the project. The first PDRI had a score of around 800, and it has decreased to the score of 750, and in the final PDRI has a score of around 700. Even the PDRI score is higher than typical score of 200. The decrease in PDRI score across all three stages shows an improvement in project definition. A score of below 200 is not reasonable for this project because many elements are not being considered, such as permitting, social issues, and site environment. Alternative design has been decided by adding a compressor and partially recycle the toluene and hydrogen. This design has met similar specification to the base case in terms of product purity of p-xylene and benzene. However, the project total for the alternate design is slightly higher than the base case. This is because we are adding the compressor. So therefore, this alternate design is not able to overcome the deficit of this plant. So it can be concluded that not to perform this alternate design.
JLP Inc. does not recommend any further implementation of this p-xylene plant to Nitline Chemicals at this time due to the extreme financial losses over time. Our negative $846 million cash flow or net present value represents too large of a deficit to come back from for this plant. A few changes could be made to increase the profit of this plant. For example, the Parex purification unit is incurring most of the capital costs. If we looked into cheaper purification methods, it could decrease the capital cost greatly. Second, we use a lot of steam in the plant, and the steam is very expensive in terms of utilities. We could also look into using the process stream instead of steam to heat or cool other parts of the process stream in heat exchanger loops. Finally, the TMB may be purified until it's 99.9% pure and sold as a product, as it has a fairly high market value. Any of these three recommendations could be studied and possibly create a positive cash flow over time, but the most likely is changing the Parex capital cost and/or the utilities. Thank you.